Hello students, in this session we will discuss Mcclay's method for slope and deflection. This method is basically used to calculate slope and deflection of a given beam at given point. So in this session we will start with the assumptions of Mcclay's method and then we will solve a numerical to calculate slope and deflection of a simply supported beam which is carrying point load. So let's start with the assumptions of Mcclay's method, and here are 6 assumptions. We can say 6 rules which we will follow for calculating slope and deflection of a given beam using Mcclay's method. Okay, so the first assumption of Mcclay's method is take origin on extreme left of the beam. So in this figure you can see beam AB is a simply supported beam and A point is the extreme left of this beam. Okay, so we will take our origin at point A for calculating sum. Okay, now next assumption is take left clockwise movement as positive and left anti-clockwise movement as negative. So here again look at this figure. This dotted line XX is a section of this beam and portion of the beam on left hand side of this section is called LHS and portion of the beam on right hand side of this section line is called RHS. Okay, and as per assumption 1 we are taking our origin at A, so we will calculate moment at LHS of this section line. It means we are calculating moment at left hand side of this section line, and whenever we are calculating moment on left hand side of the section line, then we will consider all clockwise movement as a positive and anti-clockwise movement as a negative. Now third assumption is quantity x minus a should be integrated as x minus a square by 2. Now whenever distance is multiplied with moment, quantity x minus a should be written as x minus a raised to 0. Now next assumption, when term x minus a is less than 0, it means value of x minus a is negative, then we will neglect that term. And last assumption is integration constant C1 and C2 are always written at first portion of continuous equation. Okay, so these 6 are the basic rules or assumptions that we will follow for calculating sum. Now let's calculate one numerical. Now let's solve a numerical using these assumptions. Okay, so here are the data. We need to calculate deflection under the loads for a beam loaded as shown in the figure. So as per this figure, one simply supported beam AB is given. Okay, total length of this beam is 14 meter and this beam carries 2-point load. First point load of 12 kilonewton is acting at a distance 3 meter from point A, and another point load of 8 kilonewton is acting at a distance 9.5 meter from point A. Now we need to calculate deflection under the loads. It means we need to calculate deflection of this beam at point C. It means YC we need to find out, and we need to find out deflection at point D, which is YD. Okay. Now this is also given data. Take value of E, which is Young's modulus of elasticity, is equal to 200 into 10 raised to 3 Newton per mm square, and value of I, which is moment of inertia of this beam, is equal to 160 into 10 raised to 6 mm raised to 4. Now before calculating sum, let's discuss steps that we will perform for calculating sum. So the first step is to calculate reactions RA and RB. So in this figure, you can see that reactions Ra and Rb are unknown. So first of all, we will calculate reaction Ra and Rb by applying condition of equilibrium. Then in a step number 2, we will form one differential equation. And in step number 3, we will perform double integration of differential equation. In step number 4, we will calculate value of C1 and C2, which are integration constant, by applying boundary conditions. And in step number 5, we will calculate slope and deflection at a given point of a beam. So these are the basic steps for calculating slope and deflection using Mcclay's method. In our case, we just need to calculate deflection. We don't need to calculate slope. So in our numerical, in a last step, we will calculate deflection at point C and point D. Now let's start with the first step of the sum, which is calculate reactions Ra and Rb. Now for calculating reaction Ra and Rb, we will apply condition of equilibrium sigma m is equal to 0. And we are taking moment about point A. It means summation of moments about point A is equal to 0. Now, moments are of two types, clockwise moment and anti-clockwise moment. So, we can say that clockwise moment plus anti-clockwise moment is equal to 0. Now, if we take clockwise moment as positive and anti-clockwise moment as negative, then anti-clockwise moment about point A is equal to clockwise moment about point A. Now, from this figure, you can see that this reaction Ra is passing through point A. It means moment of this reaction Ra about point A will be 0. Okay. Now, this reaction Rb is acting in an upward direction. Okay. And if I take moment of this support Rb about point A, then the moment generated will be anti-clockwise, which is equal to Rb, which is load, into distance of line of action of this Rb from point A, which is 14. So, moment of this support about point A will be equal to Rb into 14. It is anti-clockwise, so we write down Rb into 14. Okay. Now, this 12 kilonewton load is acting in a downward direction, and if I take moment of this 12 kilonewton load about point A, then the moment generated will be clockwise, which is equal to 12 load into distance. Distance is 3. Similarly, moment of this 8 kilonewton load about point A will be 8 into 9.5, which is again clockwise. Okay, so it is written as Rb into 14, which is anti-clockwise moment, is equal to 12 into 3 moment of this 12 kilonewton load plus 8 into 9.5, which is moment of this 8 kilonewton load. So if we solve this, then we get answer of Rb is equal to 8 kilonewton. Now let's apply another condition of equilibrium for calculation of Ra. So we are taking sigma v is equal to 0. It means summation of vertical forces is equal to 0. Now on this beam, two types of vertical forces are there. Supports are acting in upward directions and point loads are acting in a downward direction. So we can say that upward forces plus downward forces is equal to 0. So if we take upward forces as positive and downward forces as negative, then we can say that Rb plus Ra is equal to 12 plus 8. So we get answer of Ra is equal to 12 kilonewton. So, we completed with the first step of the sum, which is calculation of reactions Ra and Rb. Now, let's calculate step number 2, which is formulating differential equation. So here is our differential equation ei d square y upon dx square is equal to minus mx. Okay, so for formulating differential equation, first of all we need to calculate mx. Okay, and for calculating mx we need to divide this beam into three different parts. Part AC, part CD will be the second part and part DB will be third part. And we need to take section in each part and calculate moment of each part about that section line. So let us consider first part AC. So here I am taking section in part AC. Okay, so I am taking section at a distance x from point A in portion AC. Okay, so you can see that this reaction RA is acting in a upward direction, and if I take moment of this reaction RA about this section, then the moment generated will be clockwise. And as per our assumption, if I am calculating moment on left hand side of the section and if it is clockwise, then I will consider it as a positive. So moment of this RA about section line will be RA, which is 12 into x is the distance. Okay. Now similarly, if I take section in part CD and taking moment of this 12 kilonewton load about that section line, then here in this figure you can see that I took section at a distance x from point A, okay, and if I am taking moment of this 12 kilonewton load about this section line xx, then this 12 kilonewton load is acting in a downward direction, okay, which is making anti-clockwise moment about this section line. Okay, and as per our assumption, if I am calculating moment about left hand side and if it is anti-clockwise, then we will consider it as a negative. Okay, so this 12x is for section AC. Now for section CD, the moment of this 12 kilonewton will be anti-clockwise, so I will put sign negative, and moment of this 12 kilonewton load about this section line XX will be 12 in bracket distance between 12 kilonewton and this axis line, which is x minus 3. Okay. Similarly, if I take section in part DB and taking moment of this 8 kilonewton load about that section line, then the moment of this 8 kilonewton load will be 8 into x minus 9.5, which is anti-clockwise, so I will take sign negative. Okay, and if I put value of mx in this equation, then I will get final differential equation as ei d square y upon dx square is equal to minus 12x plus 12 x minus 3 plus 8 x minus 9.5. Okay, so we are completing second step for the numerical. Now let's move to the third step, which is double integration of differential equation. So first of all, we will integrate differential equation. So if we integrate this differential equation, then we will get ei integration of this d square y upon dx square will be dy by dx is equal to minus 12. Integration of x will be x square by 2 plus c1. As per our assumption, we will write down integration constant in first part of the continuous equation, plus 12 integration of quantity x minus 3. As per our assumption, we will integrate x minus 3 as x minus 3 square by 2, plus 8 integration of x minus 9.5 will be x minus 9.5 square by 2. Now if I simplify this integrated equation, then I will get final equation as EI dy by dx is equal to minus 6, which is 12 by 2, plus C1 plus again 12 by 2 is 6, x minus 3 square plus 8 by 2 is 4, x minus 9.5 square. So this is the equation we will use to calculate slope. Okay. Now let's integrate equation number 1, which is used for the slope. Then we will get integrated equation as EI. Now integration of dy by dx is equal to y. So EIy is equal to minus 6 x cube by 3, integration of x square is x cube by 3, plus integration of the C1 is C1 into x plus C2, which is integration constant, plus 6 integration of x minus 3 square will be x minus 3 cube by 3 plus 4, and integration of x minus 9.5 square will be x minus 9.5 cube by 3. And if I simplify this equation, then I will get final equation as EI into y is equal to minus 2x cube plus C1 into x plus C2 plus 2 x minus 3 cube plus 4 by 3 x minus 9.5 cube. So we are completed with step number 3. Now let's move to step number 4, which is calculation of value of C1 and C2, which are integration constant by applying boundary condition. So here we know that for a simply supported beam at both extreme end, means at end A and at end B, deflection will be 0. So if I apply first boundary condition, when x is equal to 0, deflection y is equal to 0. And if I put value of x and y, which is equal to 0, in equation number 2. Equation number 2 is for calculation of deflection. Okay. Then I will get value of C2 is equal to 0. So here if I put x is equal to 0 and y is equal to 0 in equation 2, then this term will be 0 because y is equal to 0. Now this will be also 0. C1 into x, x is 0. So this will be also 0. C2 will remain as it is. Now this quantity x minus 3. So x is equal to 0. So value of x minus 3 will be negative, and as per our assumption we will neglect this quantity. Similarly, value of x minus 9.5, if I put x is equal to 0, then we will get negative value and we will neglect it. So ultimately, by putting x is equal to 0 and y is equal to 0 in second equation, we get value of C2 is equal to 0. Now, at another end, if I apply another boundary condition, which is x is equal to 14, deflection is 0. It means when x is equal to 14, y is equal to 0, and if I put this value in second equation, then this y is equal to 0 is equal to minus 2, x is equal to 14, x cube is equal to 14 cube, plus C1 into x, it means C1 into 14, plus value of C2 is 0, so I am putting 0 over here, plus 2 into x minus 3 cube. Okay, so plus 2, x is replaced with 14, 14 minus 3 cube, plus 4 by 3 in bracket x minus 9.5 cube. So we can write down 4 by 3, 14 minus 9.5 cube. So if I solve this, I will get value of C1 is equal to 193.17, and if I put value of C1 and C2 in equation number 1 and equation number 2, then these are the final equation to calculate slope and deflection. So now for calculating slope or for calculating deflection, we need to put value of x in equation number 3 for calculating slope and in equation number 4 for calculating deflection. Now in our numerical we need to calculate deflection only, so we will use equation number 4 to calculate deflections. So now let's move to step number 5. So here, because of this load and the support condition, the beam will be deflected like this, and we need to calculate YC, which is deflection at point C, and YD, which is deflection at point D of this beam. So let's calculate deflection at C. So for calculating deflection at C, we need to use this deflection equation number 4. Okay, and we need to put value of x in this deflection equation, so we will get deflection YC. Okay, now you can see that point C is at a distance 3 meter from point A. So if I put x is equal to 3 in this deflection equation, then I will get value of deflection at point C. So let's put x is equal to 3 in equation number 4 to get YC. So we can say that EI into YC is equal to minus 6, x is 3 square by 3 plus 193.17 into x is 3 plus 2 in bracket x minus 3 cube, which is 2 in bracket 3 minus 3 cube plus 4 by 3 in bracket x minus 9.5 cube, which is equal to 4 by 3 in bracket 3 minus 9.5 cube. Okay, so here in last term, value of 3 minus 9.5 will be negative, so we will neglect this term, and if I solve this, then I will get EI into YC is equal to 525.51 kilonewton into meter cube. So YC will be equal to 525.51 upon EI. Now I am converting kilonewton into meter cube in Newton per mm cube. So I need to multiply 525.51 with 10 raised to 12. So I am multiplying 525.51 into 10 raised to 12 to get unit in Newton into mm cube. Upon if I am putting value of E and I, which is already given in a data, so value of E is 200 into 10 raised to 3 Newton per mm square, and value of I, which is also given, it is 160 into 10 raised to 6 mm raised to 4. So I get answer of YC is equal to 16.4 mm. So I can say that we will get deflection at point C is equal to 16.4 mm, which is positive. So we can say that deflection will be in a downward direction. Now let's calculate deflection at YD. So deflection at D, for calculating deflection at D, we need to put value of x in this deflection equation. So point D is at a distance 9.5 meter from point A. So for getting deflection at D, we will put x is equal to 9.5 in this deflection equation. So we will get final equation as EI YD is equal to 6 by 3 9.5 cube plus 193.17 into 9.5 plus 2 into 9.5 minus 3 cube plus 4 by 3 9.5 minus 9.5. So I will get EI YD is equal to 669.61 upon EI, and I am converting 669.61 into Newton into mm cube. So I am multiplying this with 10 raised to 12 and putting value of E and I as we put for calculation of YC, then I will get answer of YD is equal to 20.9 mm. Again, it is a positive value, so we can say that we get deflection YD in a downward direction. So, as per the data, we calculated deflection YC and YD both. So, this is the end of this session. In next session, we will solve few more numericals. Thank you.